A stochastic system is defined over a probability space consisting of a sample space, a sigma algebra, and a probability measure. The system state evolves as a measurable function from this space into a state space S. Each realization of the system corresponds to a single trajectory through S. The ensemble is the full collection of trajectories indexed over the sample space. These two objects, the individual trajectory and the ensemble, are structurally distinct and must not be conflated in system analysis. A formal system architecture distinguishes two averaging operations over the state space. The ensemble average at time t is the expectation of the state variable across all realizations simultaneously. The time average is computed along a single trajectory over the observation horizon t. These two averages operate on different mathematical structures. The ensemble average integrates over outcomes, the time average integrates over time. The ergodicity property is the structural condition under which these two averages coincide. Ergodicity is a formal property of a dynamical system's state space structure. A system is ergodic if and only if its time averages converge almost surely to its ensemble averages as the observation horizon grows without bound. This convergence is a structural property of the transition law, not a behavioral property of individual trajectories. Two convergence modes are recognized: mean ergodicity, which requires convergence in L squared, and almost sure ergodicity, which requires pathwise convergence for almost every realization. Almost sure ergodicity is the stronger condition and the one required for deterministic design guarantees. Stationarity and ergodicity are formally independent properties of a stochastic system. A system is stationary if the probability distribution of its state is invariant with respect to time translation. However, stationarity does not imply ergodicity. A system in which each realization is assigned a fixed constant value at initialization is stationary. Its distribution is identical at every time step, yet non-ergodic. The time average of each trajectory equals its initialization constant, not the ensemble mean. This constitutes a structural failure of ergodicity that stationarity alone cannot detect. The state space topology determines whether ergodicity is structurally achievable for a system. An irreducible system is one in which every state is reachable from every other state under the transition law. The state space is connected with respect to the dynamics. A reducible system has communication barriers. Some states are structurally unreachable from others, partitioning the state space into disconnected components. Irreducibility is a necessary condition for ergodicity. A reducible system cannot be ergodic because trajectories starting in disconnected components never visit the full state space, and time averages remain permanently confined to their component. Absorbing states are the canonical mechanism by which ergodicity fails in engineering systems. An absorbing state is a state from which no transition to any other state is possible. The self-transition probability equals 1. Once a trajectory enters an absorbing state, it remains there permanently. The time average converges to the value of the absorbing state, not to the ensemble mean. This constitutes a permanent structural failure of ergodicity with respect to the full state space. Absorbing states model irreversible failure modes, system saturation, and permanent constraint violations, all conditions that destroy the ergodic property required for ensemble-based performance guarantees.